Photosynthesis is a process used by plants and other organisms to convert light energy, normally from the sun, into chemical energy that can be later released to fuel the organism's activities. This chemical energy is stored in carbohydrate molecules, such as sugars, which are synthesized from carbon dioxide and water. In most cases, oxygen is also released as a waste product. Most plants, most algae, and cyanobacteria perform photosynthesis, and such organisms are called phototrophs. Photosynthesis maintains atmospheric oxygen levels and supplies all the organic compounds and most of the energy necessary for life on Earth. The most active photosynthetic tissue in aeroplanes is the mesophyll of the leaves. Mesophyll cells have many chloroplasts, which contain the specialized light-absorbing green pigments, the chlorophylls. In photosynthesis, the plant uses solar energy to oxidize water, thereby releasing oxygen, and to reduce carbon dioxide, thereby forming large carbon compounds, primarily sugars. The complex series of reactions that culminate in reduction of carbon dioxide included the thylakoid reaction and the carbon fixation reactions. The thylakoid reactions and photosynthesis take place in the specialized internal membranes of the chloroplasts called thylakoids. The end products of these thylakoid reactions are the high-energy compounds ATP and NADP, which are used for the synthesis of sugars and the carbon fixation reactions. The synthetic process takes place in the stroma of the chloroplast, the aqueous regions that surround the thylakoids. In the chloroplasts, light energy is converted into chemical energy by two different functional units called photosystems. The absorbed light energy is used to power the transfer of electrons through a series of compounds that act as electron donors and electron acceptors. The majority of electrons ultimately reduce NADP plus to NADPH and oxidize water to oxygen. Light energy is also used to generate a proton motive force across the thylakoid membrane, which is used to synthesize ATP. The transfer of electrons and protons in the thylakoid membrane is carried out vectorially by four protein complexes. Water is oxidized and protons are released in the lumen by photosystem 2. Photosystem 1 reduces NADP plus to NADPH in the stroma via the action of ferredoxin and the flavoprotein ferredoxin NADP reductase. Protons are also transported into the lumen by the action of the cytochrome B6F complex and contribute to the electrochemical proton gradient. These protons must be diffused to the ATP synthase enzyme, where their diffusion down the electrochemical potential gradient is used to synthesize ATP in the stroma. Reduced plastoquinone and plastocyanin transfers electrons to cytochrome B6F and to photosystem 1 respectively. The Calvin cycle. All photosynthetic eukaryotes, from the most primitive algae to the most advanced angiosperm, reduce carbon dioxide to carbohydrate via the same basic mechanism. The photosynthetic carbon reduction cycle, originally described for C3 species. Other metabolic pathways associated with the photosynthetic fixation of carbon dioxide, such as the C4 photosynthetic carbon accumulation cycle and the phorespiratory carbon oxidation cycle, are either auxiliary to or depend on the basic Calvin cycle. In the Calvin cycle, carbon dioxide and water from the environment are enzymatically combined with a 5-carbon acceptor molecule to generate 2 molecules of a 3-carbon intermediary. This intermediary is reduced to carbohydrate by use of the ATP and NADPH generated photochemically. The cycle is completed by regeneration of the 5-carbon acceptors. The Calvin cycle processes are three stages. First, carboxylation of the carbon dioxide acceptor ribosa 1,5-biphosphate, forming two molecules of 3-phosphoroglycerate, the first stable intermediary of the Calvin cycle. Second, reduction of the 3-phosphoglycerate, forming glyceraldehyde 3-phosphate and carbohydrate. Third, regeneration of the carbon dioxide acceptor ribulose 1,5-biphosphate from glyceraldehyde 3-phosphate. The carbon in the carbon dioxide is the most oxidative form found in nature. The carbon of the first stable intermediate 3-phosphoglycerate is most reduced, and it is further reduced in glyceraldehyde 3-phosphate product. Overall, the early reactions of the Calvin cycle complete the reduction of atmospheric carbon and in so doing facilitate its incorporation into organic compounds. The C2 oxidative photosynthetic carbon cycle rescues the carbon loss as 2-phosphoglycolate by Rubisco oxygenation activity. The dissipative effects of photorespiration are avoided in some plants by mechanisms that concentrate carbon dioxide at the carboxylation sites in the chloroplasts. These mechanisms include a C4 photosynthetic carbon cycle, CAM metabolisms, and carbon dioxide pumps of algae and cyanobacteria.